Hi everyone. Today let's start chapter 6, Counting Methods and the Pigeonhole Principle. Session 6.1, Basic Principles. There's one primary goal in this chapter. There will be 3 principles: the multiplication, addition, and the inclusion-exclusion principles. We will learn counting techniques. This means we will know how to determine how many ways an event can occur. This is critical in subjects such as probability, programming, and actuarial science. Okay, so first, the multiplication principle. Suppose you want to eat at your favorite restaurant. If you can order 3 different appetizers, 8 main courses, and 5 desserts, how many unique meals can you order? Wow, so here we have 3 kinds, right? So we have the appetizer, the main course, and the desserts. How many choices for the appetizer? We have 3 choices, right? And how many choices for the main course? We have 8. And how many choices for the desserts? We have 5. So for the different choices, we're going to multiply together. Even events, you can separate into steps, and then each step you have several choices, and then at the end, the result is going to be you multiply all the choices in each step together. So 3 times 8 times 5 equals, so we can think of 8 times 5 is 40, 3 times 40 is 120. Right, so there are 120 unique meals we can order. Okay, again, so if an activity can be completed in T successive steps, if you can complete step 1 in n sub 1 different ways, step 2 in n sub 2 different ways, step 3 in n sub 3 different ways, and step t in n sub t different ways, then you can complete the activity in n1 times n2 times n3 times nt different ways. Okay, so just multiply the choices from each step together, okay? So let's look at example. How many strings of length 4 can be formed from the letters A, B, C, D, E? So there are 5 choices, right? Is a string of length 4. So it's like we have 4 boxes. Each box will fill with either A, B, C, D, E. So each of them is 5 choices. That's why we get 5 to the 4. And let's plot this in our calculator. 5 to the 4 equals 625. So far, so good, everybody? Okay, let's continue. How many strings of length 4 can be formed if it must begin with a D? Okay, so it must begin with a D. Then the first one we know is D, so we have no choice for that. But the second one, we also have 5 choices. Third one, 5 choices. And the last one, also 5 choices. So that's why we have 5 to the third. And that is 125. So far, so good? Okay, next. How many strings can be formed if it must not begin with E? Okay, it must not begin with E. Okay, so this guy is not E. Then we have 4 choices, okay, because we can pick E. And there are total 5 choices because we cannot pick E, so there are only 4 choices for the first letter in the string. And then the second one, we have 5 choices. The third one with 5 choices. The last one, we also have 5 choices. That will give us 4 times 5 cubed. So that is 4 times 125. The answer is 500. Oh, this 0 looks like a 6. Let me rewrite it. 500. So far, so good, everybody? Okay, So let me put a remark here. So all these 3 parts of questions, we allow the letter to repeat. Okay, so all these we allow letter to repeat. What if we don't allow letter to repeat? What do we do in that case? Okay, so now let's do more. Okay, so right now, so we don't allow letter to repeat. Okay, so the letters don't repeat. How does change our answers? Okay, first questions. For string of length 4, the first one we have 5 choices, A, B, C, D, E, but then the second one, because we don't repeat after we pick the first one, then there's only 4 choices left for the second one. And then the third one, after we pick the 2 for the first 2 letter in the string, now we only have 3 choices. The last one we only have 2 choices, so that's why how many different ways? 2 times, okay, I would do 2 times 5 is 10, 4 times 3 is 12, 12 times 10, 120. So you can see there are only 120 not repeat strings of length 4. Okay, you can see much less than the original 625, and which makes sense because now we don't allow letters to repeat. Okay, next. So here, the first one start with a D, and then how many choices here? So 4 letters, A, B, C, E, right? And then next, we have 3 letters and 2 letters. So the result is 4 times 3, 12, 12 times 2, 24. So far, so good. Okay, let's continue. Okay. Now, the first one cannot start with E. Cannot start with E, so we have 4 choices. So after we pick 1, and then what do we have left? Okay, then we only left with 4 choices, right? And then next, after we pick the 2 letter, we still have 3 choices. At the end, we have 2 choices. So far, so good, everybody? Okay, so what is that? Well, that is the same as 4 times 24. So 4 times 24 equals 96. Okay, so this is the cases when we don't allow letters to repeat. So when you read the problem, you gotta be very, very careful. Do we allow the letters to repeat or not? Okay. Let's continue. Example, prove that there are 2 to the n subsets of a set with n elements. Okay, so subsets, right? I think we proved this before, okay? So what do is, okay, imagine we have a subset, okay? You want to look at all the elements in this set. Does this elements appear in the set? Okay, let's say all the elements are x1, x2, xn, and then you want to ask, does this element appear in that set? In that subset? Okay, then each one has 2 choices, either appear or do not appear. So okay, so each element either appear or does not appear in the subset. So that's why we have 2 choices. Okay, then the first element give us 2 choices, second element give us 2 choices. At the end, we have 2 choices for xn. So here we have n copies of 2 multiplied together. So this is 2 to the n. Okay, this is the easy way we talked about before. So today, I'm going to teach you another way how to think. Okay. Here, I'm gonna separate into cases. So that was method 1. Okay. I would love to show you different methods so you can compare and we can learn more. Okay, different methods teach us something new. Okay, so method 2, we're gonna separate. Okay. Oops. Into cases. First case, we pick 0 elements. Okay, let's say we want to form a subset. Okay, let's say we pick 0 elements. Next case, we want to pick 1 element and we want to pick 2 elements, etc. until we want to pick n elements. Okay, so we want to form a subset. Okay, so if we pick n elements, then it's like okay, so here it's 0 because it's like we have n elements, we pick 0 of it. So n elements, we pick 0 of it. Oh sorry, that is only 1. Okay, and this is the empty set. This symbol and choose I will so we will learn this. Okay, so we will learn these in the next session. Okay, so if you want to really figure out what this is, you can maybe like skip this part, and after we learn the next sessions, you can go back here and then watch this video again to continue with this method. Okay, and this guy is called combination and choose I. Okay, so we want to pick 0 elements and choose 0 is 1. Okay, next we want to pick 1 element, so that's n choose 1. So n choose 1 is actually n. Okay, pick 2 elements is n choose 2. Well, that is n times n minus 1 over 2. And then after that, we eventually want to pick n elements. Okay, and n choose n, it equals 1. Okay, so at the end, we add all the cases together. So n choose 0, n choose 1, n choose 2, plus plus at the end, n choose n. In fact, what is this? Well, there is a binomial theorem. Tell us that this guy is in fact 1 plus 1 to the power of n, which is 2 to the n. Well, in general, the binomial theorem, what is the binomial theorem? Let me put it here. Okay, so binomial theorem tells us a plus b to the power of n is n choose 0, a to the 0, b to the n, plus n choose 1, a to the 1, b to the n minus 1, plus plus n choose n, a to the n, b to the 0. Okay, but just in this case, our a and b is just 1, so that's why we only get the coefficients. So it's just like 1 plus 1 to the n is 2 to the n. Something related to that is you know the Pascal triangles. The simplest case is that a plus b squared is a squared plus 2ab plus b squared. The Pascal triangle form with you put 1 at the edges, and then you sum those two together, you get the number 2. So this corresponds to this formula. The next one, you're gonna sum these together, and actually this line corresponds to a plus b cube. Okay, so a plus b cube is a cube plus 3a squared b plus 3ab squared plus b cube. Okay, and so if you're interested, please come to see me. I can explain to you more about this. This is Pascal triangle. So let me put it down here. Pascal's triangle. Okay, which is this guy. It's a triangle shape. All right, let's continue. The addition principle. How many 8-digit binary numbers that begin with 111 or 101? Okay. Well, in this case, it's like we separate into cases because it's OR. So we want to find the number that start with 111, and then we want to find the numbers of 8 digits and binary numbers that start with 101, and then we add those two numbers together. Okay, so let's see. We have 8 digits binary numbers, right? And then this guy start with 111, and then how many digits left? We have 5 digits left. Each of them could be 0 or 1, so 2 choices. So that's why we have 2 to the 5 is 32. So 32 numbers that start with 111. How about start with 101? So actually, it's the same thing, right? Each choice we can have 0 or 1, and this is still 2 to the 5 together, and that's 32. So that's why the total number of 8-digit binary numbers begin with 111 or 101 equals 32 plus 32, which is 64. Okay, so suppose x1 xn are sets that the I set xi have elements ni. If the set x1 xn is pairwise disjoint family, the number of possible elements that can be selected from x1 or xn is gonna be the sum of n1, n2, nn. Okay, and what would be the number of elements in the union of the set? Okay, which is this. Okay, the union of sets, we just add those numbers together because they are pairwise disjoints. What is pairwise disjoints? Do you remember? Which means if I pick any pair of them when we take the intersections, is an empty set. Okay, so all of these sets, they don't have common elements. Like our previous examples, the string start with 111 and the string start with 101. They're different strings. Okay, they don't have any intersection. Okay, so let's continue. In how many different ways can I select 2 books of different subjects if there are 4 distinct computer science books, 5 distinct mathematics books, and 7 sociology books? Okay, so let's see here. We want to select 2 books from each subject, right? Okay, so how many possibilities are there? Okay, 2 books from different subjects. So let's separate into cases. Okay, we need 2 different subjects. We can have CS and let me see. Let's use CS. So we can have CS and math. We can have CS and sociology. We can have math and sociology. Of course, the order doesn't matter, right? You can have math and computer science is the same as computer science and math. Okay, so in the first case, we have 1 book of computer science and 1 math book. So how many choice for computer science? Well, 4. How many choice for math books? 5. So 4 times 5 is 20. So far, so good, everybody. Okay, second, we have computer science and sociology. So we have 4 oops. Let me see, I pressed the wrong button. Okay. Alright, let me save it first. Okay, so we have 4 computer science and 7 sociology books. Together give us 28. And then next we have math and computer science. We have, math and sociology. We have 5 math books and 7 sociology. So that gives us 35. Okay, and there are different cases. So at the end, we add those numbers. Okay, so computer science, math, and sociology. Okay, this is what it means. So 20 plus 28 plus 35. What is this? Okay, so we can type this in our calculator. The result is 83. Do you have the same answer? Alright. Okay, let's continue to our next example. So I strongly recommend you to pause the video and try the problem first. And then after you're done, we can check our work together. Are you done? Let's check it. I have 6 balls, all of different color. Red, blue, yellow, green, purple, orange. Okay. I want to select 3 different balls and put them in position 1, 2, and 3 on the board. Part A. In how many different ways can this be done? Okay, so let's see. So on the board, there are position 1, 2, 3, right? So we want to pick 3 different balls. So the first position, how many choices are there? We have 6 colors, so we have 6 choices. But then the second position, how many choices are there? We want to pick different balls, right? So there's only 5 choices left. And then the last position 3, how many choices left? Because we already picked 2 colors, now we only have 4 colors left. So, and we multiply them together because they're different steps, right? So when we multiply them, we get 120. So far, so good, everybody. All right, let's continue. Part B. In how many different ways can this be done if red or blue must be in position 1? Okay, position 1, it must be red or blue. So red or blue, then there's only 2 choices. And position 2, after you pick the first color, there are 5 choices left. Position 3, after we pick 2 colors, there are 4 choices left. So the answer is 40. So far, so good, everybody. Okay, let's continue. Part C. Okay. Part C. In how many ways can this be done if orange must be selected? Okay, so orange must be selected, but we have 3 positions. Which position do we mean, right? So, is it in position 1 or in position 2 or in position 3? That's why we need to separate into steps. So if the problem is more complicated, it's better to separate into steps or separate into cases. So step 1, okay, step 1, we want to place the orange color. Okay, so, and there are 3 choices. Okay, position 1, position 2, position 3, right? This is step 1. All right, next, step 2. After we fill in the orange in a position, then we can pay the remaining 2 positions Okay, so there are only 2 positions left. The first, we have 5 choices because we already used orange. Then we only have 5 choices of other colors left. And then next, we have 4 colors left because we have paid orange and one of the color. Okay, so in this step, we have 20 different ways. Alright, finally, because there are different steps, so the total is gonna be the number in each step. We multiply them together, so that is 60. Okay, so part C, we have 60 different ways. Let's continue. Part D. In how many different ways can this be done if both red and orange has to be selected? Okay, so we must select red and orange. So let's separate the steps. I would say step 1, let's place the red. Okay, let's place the red in the positions. And there are 3 positions, so 3 choices. Okay, and step 2, after we place the red, let's place the orange. Well, how many choices? Because we already placed the red. I don't know, the red may be in the for position 1 or 2 or 3, but I know there are only 2 positions left. So because there are 2 positions left, we have 2 choices. And step 3, so after we place the red and the orange, so we only have 1 position left. And how many colors left? We have 6 colors. We have already picked 2, so 4 colors left. Oh, so there are 4 choices here. Okay, what is the total? Well, the total is, you see different steps. Whatever number you get from these steps, multiply them. So the first step, 3 choices. Second step, 2 choices. Step 3, 4 choices. So the answer is 24. So that is part D. So far, so good, everybody? So remember to separate into steps. If you separate into steps, then the number is gonna be the multiplication, the product of the choices you get from each step. But if you separate into cases, then the result is gonna be you add the number in different cases together. Okay, so steps corresponds to products. Cases corresponds to sum. So far, so good, everybody? Alright, let's continue. The inclusion-exclusion principle. Okay, so the union of X union Y, okay, equals the number in X plus the number in Y minus the numbers of their intersection. Why is that? Let me show you here. Let me show you a Venn diagram. Okay, so we have, this is X, this is Y. Okay, so how do you count X union Y? Okay, so you want to count this guy, right? You want to count this shaded region. So there are 3 regions, but each of them you only want to count it once. So X, when you count X, you count this region and you count this region as well, right? When you count the number Y, you count this region, you count this middle guy again. So do you realize the middle guy? So this middle guy is X and Y. Do you see you counted 2 times? That's why you need to subtract 1 copy back. That's why you have the number in X plus the number in Y minus the number in their intersection, because the intersection you counted twice, so you want to subtract it back. And this is similar like what we did in our counting. If sometimes we counted twice, then we need to subtract it back. So far, so good, everybody? Okay. I also want to emphasize what we just said, addition. Addition is just like a special case of this inclusion-exclusion principle, because in our addition cases, our intersection, we require the set to be disjoint, so the intersection is empty, so the number of elements in their intersection is 0. So that's why in that case we don't only have the addition. So addition is just a special case of these inclusion-exclusion principle. So far, so good, everybody? Alright, let's continue. Of the students outside here at Indiana Tech, 150 students are wearing coats, 120 are wearing hats, and 50 are wearing both. How many students are outside? Okay, so we can say wearing coats is X, wearing hats is Y, they're wearing both is X and Y. Then by our principle, student outside is like X union Y. Okay, so that equals number of X plus number of Y minus number of X and Y. Number of X, that's 150. Number of Y, that's 125. Minus 15, wearing both. So that is, we can do 150 minus 50, that's 100. 100 plus 125 is 225. So far, so good, everybody? Okay, let's continue. Of 175 students at Indiana Tech surveyed, 100 take Calculus 1 and 110 students take English 101. How many of them take both? Okay, so what is this? Alright, so if we say take calculus is like X, take English is like Y, and then the total student like X union Y is 175, right? So we use this principle. The number of the union is 175 equals student take calculus 1, so that's 100, and then student take English 101, so that's 110, minus the students they take both. Okay, so what do we get? Well, we can move this to the left. Then we have X intercept Y equals, and we can have 100 plus 110. We can subtract 175, right? So that's why we get 210 minus 175. The answer is 35. So far, so good, everybody? Okay, so you can see the first part 1, where we know the union, we know the X, we know the Y, and we're looking for the number of both. But second problem, we know the union, I want to say example 1, we know the number of X, number of Y, and we know the number of intersection. So we want to find the number of their union, okay? Problem number 2, we know the number of X, the number of Y, and we know the number of the union. We want to find the number of intersection. So you can see we can play with it this way, in different direction. Know the union, and then find the intersection. Know the intersection, then we can find the union. So far, so good, everybody? And in fact, there is inclusion and exclusion principle for 3 sets. Let me see. Okay, so this is a couple, like a remark or extent. So this is the inclusion-exclusion principle for 2 sets, right? We actually have the inclusion-exclusion principle for 3 sets. So you can think of this as the extra, okay, of let me see. I'm gonna put it right here. Okay, so inclusion-exclusion principle for 3 sets. So how does this work? Let's say we have A, B, C, right? So A, B, C. So A union B union C equals, first of all, we do A. So A is this guy, this guy, this guy, this guy, right? Plus B. B is this guy. But this guy again, and this guy again. See, some region we counted twice. And we plus C. C is this guy, this guy, this guy, this guy. So you can see some region we counted twice, some region we counted 3 times. So for the region we double counted. So minus A and B. What is A and B? Let me change a different color so you can see more clear. Okay, so minus A and B. A and B is this region and this region. Okay, minus A and C. Well, A and C is... okay, let me put that there. Is this region and this middle region. Minus A... B and C. Okay, so B and C. B and C is this region and this region. Okay, now can you see this region, and this region? We only counted 1, so that is good. But the middle region, do you see the middle region? We have 3 add and we have 3 minus, so it means we didn't count it. So we need to add it back. Let me see. Okay, so we need to add it back. So we need to add A and B and C, and that's the middle region. We need to add it back. Okay, so this is why it's called inclusion-exclusion principle. So you include all of them, then you exclude some of this, and then you include. So it's gonna be alternates, add, minus, and add. So this is what happened when we have 3 sets. In general, if we have more than 3 sets, well, you're gonna first add the number of elements in one set, and then you're gonna subtract the number of elements in the intersection of 2 sets. Okay, so any pair of intersection of 2 sets, and then you're gonna add the intersections of 3 sets, and then you're gonna subtract the intersection of 4 sets. You're gonna add the intersection of 5 sets, etc. So this is the pattern. Okay, it's inclusion-exclusion principle. So far, so good. All right. So I hope your notes has enough space for it. Okay, and that is 6.1. We will continue on 6.2 in the next video. Have a nice day. Bye.